this is Captain Chaudhari. In my series of videos on basic ship stability calculations, I was doing bilging, that is damage stability calculations, and I had finished the midship compartment bilging. So various locations of the watertight flat we had considered. We had considered various permeabilities, including a liquid that was there in the double bottom. Now, I want to do a numerical which probably looks like an end compartment bilging or intermediate compartment bilging, but actually the question is not based on the end compartment bilging calculations. Here is a question where we need to find out what is the permeability. Like, you know the initial 4.5 drafts of a box vessel, you also know the final 4.5 drafts of the box vessel, but you don't know what is the permeability. So we work on this principle that the intact underwater volume after damage does not change. Once again, the basic definition of constant displacement method, that if the compartment to be damaged is void of liquid, that means it has either dry rigid cargo or it is empty, then after the damage, the displacement of the vessel does not change. Water which comes in the compartment is not property, or it is not exercising any weight on the ship. It is property of the sea, which means that the displacement, if it is not changing, the kg and lcg also will not change, and also the intact underwater volume which provides the buoyancy to support the displacement will also not change. So here is a question from my book, Complete Ship Stability. There is a box vessel 100 meter long, and it is 12 meter in the breadth. Yes, this ship is floating at an even keel draft of 6 meters. On the forward side, there is a compartment that is 10 meters long. It is filled up with some homogeneous cargo, and the damage occurs to this compartment. And after damage, what happens is, of course, if the damage is off, there will be trimming of the vessel afterwards. And the final drafts which were found were 7.03 here and 5.53 over here. This is 7.03 and that is 5.53. Now, what actually happens is, the vessel was floating at the peck line that you see is a 6 meter even keel draft. Then we will understand the change of draft in 2 stages. In the first stage, the vessel has bodily sinkage, so that is indicated by this distance. The center of flotation also would shift from a point which was actually 50 meters from either end to a point which is on the new water line but away from the damage. So this is what is the shift of center of flotation. Now, as I said, we'll be working on the principle that the intact underwater volume does not change after the damage. Let us say the permeability is P. P is the permeability. So permeability goes with the loss. So can I say if P is a fraction representing permeability, then 1 minus P is what is still intact, right? If P is permeability, then 1 minus P is still intact. Before damage, what was the underwater volume? That was 100 into 12 into 6, that is 7,200 meter cube. This was the underwater volume before damage. Now, after damage, what happens is, we look at a water line that is 7.03 and 5.53. We can divide the underwater volume in 2 parts. One is we can call it V1 over here, and another one we will call it V2. Now let us find out this volume V2 first. Volume V2, we need to find out what is the draft at this point. The change of draft from forward to aft is 1.5 meters over a distance of 100 meters. So 100 meters accounts for change of draft of 1.5 meters. So 10 meters will account for the change of draft of 0.15 meters. So the draft at this point will be 7.03 minus 0.15, that is equal to, that's going to be 6.88 meters. Now, how to find out the underwater volume in the forward 10 meters? So I suggest we find out the area of this trapezium and multiply by 12. So area of trapezium is mean of the parallel side, so 7.03 plus 6.88 divided by 2 and multiply by the distance between the parallel side, and if I want volume I multiply by 12, but I know that this portion fully is not supporting the buoyancy. So what is the intact part of this part? What is the intact part of this volume? So I'll multiply by 1 minus P, because P goes with the loss, 1 minus P should go with the intactness. So this is V1. Okay. Now V2 will be 6.88 on the same line plus 5.53 divided by 2 multiplied by 90, and if I want volume I multiply with the breadth, that is 12. So V1 plus V2 should be equal to, V1 plus V2 should be equal to 7,200. So let us solve this. 7.03 plus 6.88 equals divided by 2 equals into 10 equals into 12, that is 834.6. 834.6 in bracket 1 minus P, and over here it is 6.88 plus 5.53 equals divided by 2 equals into 90 into 12, and that gives me 6701.4. 6701.4 meter cube. Now this is V1 and this is V2, and V1 plus V2 should be equal to 7,200. So 834.6 minus 834.6 P. I bring it over here. This expression is over here. Plus 6701.4 is equal to 7,200. So 834.6 P should be equal to 834.6 plus 6701.4 minus 7,200. So 6701.4 plus 834.6 equals minus 7,200 gives me 336, and 336 divided by 834.6 gives me 0.4025. So P I get as 0.4025. So P is a fraction. So the permeability is 40.25%. So this is how we are using the principle. This is how in this question we have used the principle that intact underwater volume in a constant displacement method does not change after the damage.